Specific latent heat of transformation. In the video on specific heat capacity, we derived the relationship between a heat transfer and the resulting change in temperature of a substance. But adding heat, for example, does not always have to be associated with an increase in temperature. This is generally the case when the state of matter of a substance changes. This is because in these cases the temperature usually remains constant despite the addition or removal of heat. The relationship shown between a heat transfer and a change in temperature obviously no longer applies in the case of phase transitions. Phase changes include, for example, melting, which leads from the solid to the liquid state. There is also a phase transition known as vaporization, in which a liquid substance changes into a gaseous state. Depending on the ambient conditions, some substances also undergo a phase transition that leads directly from the solid to the gaseous state. This is called sublimation. For all these phase transitions, reversal processes also exist in each case. The reversal process of melting is called freezing or solidification, and that of vaporization is called condensation. The reversal process of sublimation is called desublimation or deposition. During all of these phase transitions, there is usually no change in temperature despite a transfer of heat. We will discuss this in more detail in the following. Let us first take a look at the vaporization of water in a pot as an example. If we place the pot with water on a stovetop, we first observe the usual behavior that the temperature increases due to the absorbed heat. However, if the water starts to boil when it reaches the boiling point, then no further increase in temperature is observed despite the heat that continues to be supplied by the hot plate. The same behavior is observed when heating ice cubes from a freezer. At first, the temperature will rise due to the heat added by the surroundings. However, when the ice begins to melt, the temperature will not rise any further as long as the melting process continues. Only after all ice has melted, the temperature starts to rise again. The same situation also occurs in the reverse cases, that is, during solidification and condensation. Despite the removal of heat, the temperatures remain constant until the phase change is complete. Such constant temperatures at phase transitions are a typical behavior of pure substances. The reason why the temperatures remain constant during phase transitions is due to the changing binding energies when the state of matter changes. During melting or vaporization, the absorbed heat energy is no longer used to increase the kinetic energy of the molecules, and thus to increase the temperature of the substance, but the energy is used to break the relatively strong bonding forces, thereby causing the change in the state of matter. A certain amount of heat is therefore required to cause the phase transition, which is not manifested in a change in temperature but results in a change in the state of matter. In the case of vaporization, this amount of energy required to change the state is referred to as the heat of vaporization or enthalpy of vaporization. Respectively, one speaks of the heat of fusion or enthalpy of fusion, if one is dealing with the heat required to melt a substance. In reference to the Latin term latare, which means to lie hidden, this heat of transformation is also called latent heat because it is not noticeable by a change in temperature. How much heat energy is actually required to completely vaporize a substance at its boiling point depends to a decisive extent on how much liquid is to be vaporized. For example, if you want to completely vaporize 1 kilogram of water at its boiling point of 100 degrees Celsius, a latent heat of vaporization of 2,257 kilojoules must be added. If, on the other hand, only half the amount of water is to be vaporized, then only half the heat is required. However, if the mass to be vaporized is twice as large, then twice as much heat of vaporization is required. The heat of transformation necessary to completely vaporize 1 kilogram of a substance at its boiling point is also referred to as the specific latent heat of vaporization or specific enthalpy of vaporization. For water, the specific heat of vaporization thus has the value 2,257 kilojoules per kilogram. Multiplying the specific heat by the actual mass to be vaporized gives the total heat of transformation to be added for completely vaporizing the liquid. Note that this heat of vaporization does not include the amount of heat required for heating to boiling temperature. The heat of vaporization always refers only to vaporization at boiling temperature, and does not include the heating process. The heat required for heating to boiling temperature must be determined separately on the basis of the specific heat capacity of the substance. Using water as an example, the heat of vaporization required to vaporize a certain amount of water will be determined experimentally in the following. For this purpose, water is first heated to boiling temperature using an immersion heater with a power of 500 watts. The vaporization of the water mass over time is then observed using a balance on which the entire experimental setup is placed. To carry out the experiment, the stopwatch is started at any point in time, while at the same time the balance is set to 0. As time progresses and heat is added, more and more water vaporizes. Finally, after 8 minutes, a total of 96 grams of water have vaporized. The supplied heat of vaporization during this time can be determined by the electrical power of the immersion heater, which is completely converted into thermal power. Thus, with an output of 500 watts, 500 joules of heat are emitted by the immersion heater every second, and the water is vaporized with this amount of energy. If the electrical power is multiplied by the operating time of the immersion heater, the total heat emitted by the immersion heater is obtained, which in the ideal case is completely used for vaporization and thus corresponds to the heat of vaporization. In the present case, after a time period of 8 minutes, which is 480 seconds, a total of 240 kilojoules of heat was transferred to the water, resulting in a total of 96 grams of water being vaporized. The specific latent heat can now be determined from the quotient of the heat of vaporization and the vaporized mass. This results in a specific heat of vaporization of 2,500 kilojoules per kilogram. The literature value is somewhat lower with 2,257 kilojoules per kilogram. This is due to the fact that the heat emitted by the immersion heater does not completely benefit the vaporization of water. Some of the heat is also used to heat the vessel and is thus transferred to the surroundings. Therefore, a smaller amount of heat is required for vaporizing the water than the heat emitted by the immersion heater, which leads to a lower specific heat of vaporization than calculated. Let us consider an example to deal with the specific heat of vaporization. 2 liters of water at 20 degrees Celsius are to be completely vaporized in a pot standing on a stovetop. How much heat must be added in total? To calculate this, we first use the specific heat capacity to determine the heat required to heat the water to boiling temperature. With a specific heat capacity of 4.2 kilojoules per kilogram and Kelvin, a mass of 2 kilograms, and a temperature change of 80 Kelvin, this results in a heat energy of 672 kilojoules. Now we determine the required latent heat for complete vaporization at the boiling point. With the specific heat of vaporization of 2,257 kilojoules per kilogram, and a mass to be vaporized of 2 kilograms, we obtain a heat of vaporization to be added of 4,514 kilojoules. The sum of the heat required for heating of 672 kilojoules and the heat of vaporization of 4,514 kilojoules finally gives the total heat to be added of 5,186 kilojoules. What is interesting is the comparison of the amounts of heat required for heating and vaporization. For the vaporization itself, more than 6 times the amount of heat is required than for heating. This is due to the particularly high specific heat of vaporization of water. The table shows the specific latent heats of transformation at their respective boiling points for selected substances. Like the specific heat capacity, the specific heat of vaporization for water is also relatively large compared to many other substances. The large specific heat of vaporization of water is one of the reasons why it is particularly suitable for firefighting. When water is poured onto the fire site, the water is not only heated, but vaporized. Due to the large latent heat, however, a great amount of heat is absorbed by the water in the process. This heat energy is supplied by the fire. This in turn means that the vaporization of the water removes a lot of heat from the fire site. As a result, the fire site cools down and the temperature drops. If the temperature finally falls below the ignition point of the burning material, the fire goes out. If the water did not vaporize when fighting a fire, but only heated up, then the water would not remove the enormous heat energy from the fire site due to the lack of heat of vaporization. The water would therefore by no means have the cooling effect and thus the desired extinguishing effect. The vaporization of the water is therefore essential when it comes to extinguishing a fire with water. In fact, the excellent extinguishing effect of water is not only due to the great amount of heat of vaporization. The fact that water expands strongly during vaporization also plays an important role. 1 liter of liquid water, at constant pressure, becomes about 1,700 liters of water vapor. This enormous increase in volume during vaporization displaces the oxygen necessary for combustion from the fire site and the fire suffocates. This happens particularly effectively when the liquid water is atomized into fine droplets and sprayed onto the fire site. Let us consider another example of how to use the latent heat. In a bucket there are 3 liters of water at a temperature of 20 degrees Celsius. We now place a glowing 6 kg steel block with a temperature of 1200 degrees Celsius in the water. The question is how many liters of water are vaporized when the steel block is cooled down to 400 degrees Celsius in water. For the sake of simplicity, we assume that heat is only transferred between the steel block and the water, and thus heat losses are neglected. We first calculate how much heat has to be removed from the steel block in order to reduce its temperature from 1200 to 400 degrees Celsius. To do this, we need the specific heat capacity of steel, which is 0.5 kilojoules per kilogram and Kelvin. The given formula, which describes the relationship between mass, temperature change, and heat, is valid in this case without further limitations, since the state of matter of the steel block does not change during cooling. If we put in the mass of 6 kilograms and the temperature change of 800 Kelvin, we get a heat of 2,400 kilojoules, which was obviously removed from the steel block during cooling. This heat energy was actually removed by the cooler water, which absorbed this amount of heat. As a result, the entire amount of water first heated up to boiling temperature and was then partially vaporized. The heat required for heating to boiling temperature is obtained from the specific heat capacity of water. The 3 kilogram mass of water was heated from 20 to 100 degrees Celsius, which means by 80 Kelvin. We thus get a heat energy of 1008 kilojoules with which the water was heated to boiling temperature. According to the previous calculation, however, a total of 2400 kilojoules of heat is removed from the steel block and thus transferred to the water. This is due to the fact that the remaining amount of heat was dissipated through vaporization. The difference of 1392 kilojoules was therefore used for vaporizing the water. We can now use the specific latent heat of the water to calculate how much mass was vaporized with this remaining heat. After solving the given equation with respect to the mass, and inserting the values, we obtain a vaporized mass of water of 0.62 kilograms. Finally, we would like to calculate the maximum amount of water that can vaporize. To do this, we must first think about the minimum temperature to which the steel block can drop. Basically, the vaporization process will continue as long as the steel block can transfer heat to the water. This will only be the case if the steel block has a higher temperature than the water. Once the temperature of the steel block reaches the temperature of the boiling water, the heat transfer and thus the vaporization will stop. Therefore, the temperature of the steel block at the point where vaporization cannot proceed any further is 100 degrees Celsius. Starting from the initial temperature of 1200 degrees Celsius, the steel block thus cools down by a maximum of 1100 degrees Celsius. If we put in this change in temperature into the given formula, we get a heat of 3300 kilojoules, which are removed from the steel block until the end of vaporization. On the one hand, this heat energy is used to heat the water to boiling temperature, and on the other hand, the remaining amount of heat is used to vaporize the water. We have already determined the amount of heat required for heating to boiling temperature in the previous example. It is 1008 kilojoules. The remaining heat is therefore 2292 kilojoules and is used for partially vaporizing the water. If we put in this heat of vaporization into the formula already derived before, we now get a water mass of 1.02 kilograms, which vaporizes at most. Let us now take a closer look at the melting of a substance and the required heat of fusion. As an example, the melting of frozen water is considered. As with vaporization, melting can also be described by a specific latent heat of transformation, which in this case is called the specific heat of fusion. In the case of water, the specific heat of fusion has a value of 334 kilojoules per kilogram. This means that at the melting point of 0 degrees Celsius, a heat of fusion of 334 kilojoules is required to completely melt 1 kilogram of ice. If the amount of ice to be melted is twice as large, twice as much heat has to be added. Thus, the product of the specific heat of fusion and the actual mass to be melted indicates the total heat of fusion to be absorbed. The table shows the specific heats of fusion of selected substances at their respective melting points. Note that the heat required for heating to melting temperature must again be determined separately with the use of the specific heat capacity. Using frozen water as an example, the heat of fusion required to melt a certain amount of ice will be determined experimentally in the following. For this purpose, frozen ice from the refrigerator is placed in an electrically heated vessel. The vessel should be as thermally insulated as possible so that the melting is due exclusively to the heating power of the heating coil and not to the heat supplied by the warmer surroundings, which would normally cause the ice cubes to melt. The supplied heat of fusion is determined, as with the immersion heater, by the electrical power of the heating coil of 25 watts, which is completely converted into heat. The melted ice is collected through a small hole at the bottom of the vessel. A balance can be used to determine the amount of ice that has melted after a certain amount of heat has been added. The specific heat of fusion can then be determined from the quotient of the heat of fusion and the melted ice mass. In the present case, after a period of 12 minutes, or 720 seconds, a total of 18 kilojoules of heat was transferred to the water, resulting in a total of 50 grams of ice being melted. From the quotient of heat of fusion and melted mass, a specific heat of fusion of 360 kilojoules per kilogram is obtained in this way. The literature value is again somewhat lower with 334 kilojoules per kilogram. Again, this is due to the fact that the heat emitted by the heating coil does not completely benefit the melting of the ice and is thus transferred to the surroundings as heat loss. A smaller amount of energy is therefore required to actually melt the ice than calculated by the heat emitted from the heating coil, resulting in a lower specific heat of fusion. Let us now take a closer look at the reverse phase transitions. For this purpose, we will first deal with the condensation of a gas. As already explained, during vaporization the heat of transformation was used to break the intermolecular bonding forces in order to make the phase change possible. The energy absorbed is now contained in the gas itself, in the relatively high kinetic energies of the molecules. These wildly flying molecules prevent the particles from permanently binding to each other due to their high kinetic energy. One can imagine the situation illustrated with magnets colliding with each other at high speeds. Due to the high kinetic energies, the magnets will just bounce off each other. Thus, in this high energy state, no binding forces can become permanently effective. The energy in the gas must therefore be significantly reduced if the substance is to liquefy again. This is done by removing heat of condensation so that the bonding forces can become effective again and the condensing substance remains permanently liquid. Here, too, the condensation temperature, equivalent to the boiling point, remains constant until the substance is completely liquefied. From an energetic point of view, it becomes clear that the heat of vaporization previously required for vaporization must now be removed in the form of heat of condensation. If a different amount of energy were dissipated during condensation than was supplied during vaporization, then complete vaporization followed by condensation would either destroy energy or create it out of nothing. Both contradict the law of conservation of energy. The specific heat of condensation therefore has the same value as the specific heat of vaporization, so that for a mass to be condensed, the same amount of heat must be removed as was added during vaporization. The heat of condensation to be removed in the case of gaseous water is usually caused by cooler objects with which the water vapor comes into contact. The latent heat is transferred to the cooler object on which the water condenses. Due to the very high specific heat of condensation of water, this usually involves very high amounts of heat. For this reason, burns from water vapor are usually much more painful and dangerous than burns from liquid water due to the enormous heat transfer, even though the same temperature of 100 degrees Celsius is present in both cases. By the way, this is also the reason why the perceived temperature rises sharply when water is poured over the hot stones in a sauna, because then the vaporized water condenses on the skin and enormous amounts of latent heat of condensation are absorbed by the relatively cool skin. As with condensation, the freezing process can also be characterized by a specific latent heat, the so-called specific heat of solidification. For the energetic reasons already explained, the heat of fusion used for melting corresponds to the heat of solidification that must be removed for freezing. Specific heat of fusion and specific heat of solidification thus have the same value. During freezing, the temperature again remains constant until the solidification process is completely finished. This is used, for example, when growing fruit is exposed to frost on cold nights and is in danger of freezing. The harvest of entire vineyards or other plantations is in danger of failing. As paradoxical as it may seem at first, the solution is the freezing of the plants by sprinkling with water. Sprinklers for frost protection do not use warm water for any heating of the plants, but ordinary tap water. After all, sooner or later the warm water would freeze anyway. And in fact, one uses just this freezing of the water for the frost protection of the sensitive plants. This is because as long as the freezing continues, the temperature does not drop below 0 degrees Celsius, even if the ambient temperatures are below freezing. The plant is thus protected from lower temperatures that would otherwise cause the cell water in the plant to freeze. Note that the freezing point of the cell water of plants, and also of most other living organisms, is about -2 degrees Celsius, which is somewhat below the freezing point of water anyway, due to the substances dissolved in it. The plants thus have a kind of natural frost protection. Since the temperature of the water on the plant does not drop below 0 degrees Celsius during freezing, the cell water inside the plant remains liquid. The large specific heat of solidification of water is particularly important in this context. This is because the large value means that a great amount of heat has to be removed for the freezing. The solidification process therefore takes a relatively long time, so that the temperature does not drop below 0 degrees Celsius for a long time. For example, 334 kilojoules of heat must be removed to solidify 1 kilogram of water. This amount of energy could also raise the temperature of 1 kilogram of water from 20 to 100 degrees Celsius. This comparison clearly shows how much heat must be removed for freezing. Therefore, the process of freezing takes a long time. Of course, this principle of frost protection works only as long as the freezing process continues, and thus the temperature inside the plant does not fall below 0 degrees Celsius. Therefore, this process must be maintained by constant sprinkling with water as long as there is a risk that the plant will be destroyed by frost. If, on the other hand, the process were interrupted, the water on the plant would freeze completely. The temperature of the plant would then drop below 0 degrees Celsius and the plant would eventually freeze to death. Besides melting and vaporization, there is also the phase transition of sublimation, which leads directly from the solid to the gaseous state. An example of sublimation is frozen CO2, also called dry ice. Dry ice changes directly from the solid state to the gaseous phase without liquefying. This is the reason why it is called dry ice. In both sublimation and the reverse process of desublimation, certain amounts of latent heat must be added or removed. These are described quite analogously to the other phase transitions by the use of a specific latent heat of transformation, which in this case is referred to as the specific latent heat of sublimation or deposition. Under certain conditions, sublimation can also be observed with frozen water. If the air is sufficiently dry and cold, the frozen water also changes directly into the gaseous state without liquefying. From an energetic point of view, sublimation can be considered as a process in which melting and vaporization take place simultaneously. The specific heat of sublimation is therefore equal to the sum of the specific heat of fusion and the specific heat of vaporization. I hope you enjoyed the video and found it helpful. Thanks for watching.